Hi, um, this is a presentation for the wireless communication course project. My name is Abhilash Bangalore Ravi, UFID 05654854. I'm going to be talking about the comparison of modulation techniques for OFDM on real world signals. Firstly, let us talk about the motivation to choosing this project. In today's world, there is a huge demand for providing multimedia and broadband services on wireless systems. Many of the applications involving multimedia broadband services include live streaming of video, music, and audio concerts, etc. Here, the emphasis is not only on high bitrate of data but also on maintaining the quality of service standards that are supported currently by wired networks. When we think of wireless communication, a characteristic of such a wireless system is that of multipath reception. The signal at the receiver consists of two types of waves. One is a direct line of sight radio wave, and another is a set of multiple reflected radio waves. What happens is that these reflected waves at the receiver are not time synchronized. That is to say that all the reflected waves do not arrive at the same period. Such waves will interfere either constructively or destructively, resulting in a phenomenon that we call as intersymbol interference. Such interference can lead to degradation or poor performance in the network. Several techniques can be used to reduce intersymbol interference. One of them is known as adaptive equalization. Adaptive equalization as a technique can reduce intersymbol interference, but at the cost of increased system and hardware complexity, as adaptive equalizers are expensive to build and it also increases the complexity in the receiver. Wireless broadband multimedia services require high bit rate of transmission, usually to the order of several megabits per second. However, the delay time of the waves in multipath reception is usually greater than one symbol time or one symbol period. Now let us introduce the concept of OFDM. OFDM stands for orthogonal frequency division multiplexing. OFDM can counter the menace of intersymbol interference. OFDM has gained incredible attention in recent years and is widely used in various standards such as the 802.11a wireless LAN and the 4th generation long-term evolution or LTE networks. Basically, OFDM is a multi-carrier transmission scheme. A high data rate serial data stream is split into multiple low rate data streams. Each substream is then modulated subsequently on a separate carrier. What happens in OFDM is that once you divide the data into several bit streams, each subcarrier is modulated at a low symbol rate, and finally the data rates that are obtained are similar to conventional single carrier modulation schemes in the same bandwidth. The main advantages of OFDM are that it simplifies the receiver design as in comparison to using an adaptive equalizer to combat intersymbol interference. And due to multipath phenomena or fading, only a few of the subcarriers are affected, which can easily be corrected by the use of some error control coding. Now let's discuss the basics of OFDM. An important aspect of OFDM is to maintain orthogonality of the carriers. As we look in the figure below here, the difference between a conventional non-overlapping multi-carrier technique and the orthogonal or overlapping multi-carrier modulation technique is shown. We can clearly see that in a non-overlapping multi-carrier technique, the subcarriers are separated in the frequency domain. And what happens is, to avoid the inter-carrier interference or adjacent carrier interference, we usually end up using some sort of frequency guard bands This will reduce the spectral efficiency and the available bandwidth is not used completely. However, this problem is tackled when overlapping multicarrier modulation technique is applied. The subcarriers can overlap and still there cannot be any sort of adjacent carrier interference. This can be achieved only when the subcarriers are made orthogonal to each other. Two signals are said to be orthogonal to each other if the integral of the product of the two signals over a time period is 0. Mathematically speaking, let's consider the set of signals, set of complex exponential signals given by exponential of j2 pi fkt, which represent the different subcarriers in the OFDM signal. These signals are defined to be orthogonal if the integral expression that is given here evaluates to 0 for all values of k that are not equal to I and evaluates to 1 for all values of k that are equal to I. Here is a visual representation or a block diagrammatic view of the OFDM system. We can clearly see that once the data is input, it undergoes some sort of source coding and channel coding. The source coding is usually to remove some sort of redundancy. The channel coding is used to introduce redundancy in some controlled manner so that errors can be avoided. The next process in this is to modulate the signal. The modulation technique can be anything. It could be quadrature amplitude modulation or phase shift keying or amplitude shift keying. It all depends on the application in hand. Once the modulation is done, the OFDM symbols are then passed through an IFFT block. The IFFT block is basically a block that will convert the spectra into time domain. One of the reasons that OFDM is being touted as a future standard or a future multiplexing technique is because of the use of the FFT or the IFFT that has been made easier by the tremendous achievements done in the field of computer engineering. Once the spectra are converted into time domain, a guard interval is added. We do know that the channels are dispersive, therefore the subcarriers will not be perfectly orthogonal. Therefore, it is necessary to add a guard interval. The guard intervals can be in the form of a cyclic prefix or zero padding. Cyclic prefix is nothing but taking the end of the OFDM signal and adding it to the beginning. Once the guard intervals are added, the OFDM symbols, which are in the discrete domain, are converted into an analog signal. The analog signal is then modulated and upconverted into an in-phase and quadrature component, and it is multiplexed to form a radio signal. The radio signal is then transmitted on an RF transmitter. The entire process is reversed at the receiver, where the receiver is designed in order to synchronize the time and the carrier phase. Moving on, let's discuss the characteristics of the OFDM system. We already spoke about it before, that the use of the FFT makes it computationally efficient. And as the channels are dispersive, the subcarriers are not perfectly orthogonal, which leads to intersymbol interference again. The solution is to use a guard interval. The two methods for using a guard sequence, as discussed before, are the cyclic prefix and the zero padding. The many advantages of the OFDM, a few of them are mentioned here. One of them is that it works better for multipath since it has lower implementational complexity at the receiver. It is robust to narrowband interference, and in slow time varying channels, capacity can be increased significantly. Let's discuss the objective of the project. The objective is to build an OFDM system using various modulation techniques such as quadrature amplitude modulation or QAM, phase shift keying or PSK,